It is June of 1593. You are a 29-year-old mathematician, possessing one of the most brilliant, restless minds of your entire generation. But right now, you are merely trying to survive a scorching, oppressive summer weekend at a luxurious Italian villa in Costoza, a wealthy enclave situated just south of Vicenza. The Italian summer heat is unbearable, a heavy, humid air that simply sits on your chest. However, this specific villa, owned by Count Camillo Trento, contains a highly coveted, unique architectural feature. It holds something known as the wind room. For a wealthy noble in the Renaissance, this 16th century luxury air conditioning system was the absolute ultimate status symbol. The room is actively cooled by air, channeled through a network of large stone vents, leading up from a system of deep underground caves at the Cavoli. Down there, the temperature remains at a stagnant, chilly 52 degrees Fahrenheit all year round. Desperate to escape the sweltering heat, you and your friends decide to sleep in this wind room. You strip down to essentially nothing, lying on the beds in the dark, and finally drift off into a comfortable sleep as the cool air wafts over you. But then, while you are sleeping, a servant inadvertently opens a wider vent. The delicate balance of the room's pressure shifts. Suddenly, the flow of that damp, freezing subterranean air increases, blasting directly onto your unprotected sleeping bodies. This seemingly trivial domestic accident is where the story takes a dark, irreversible, and horrifying turn. You wake up a few hours later, and your body is in total revolt. You are violently ill, and this is no mere summer cold. You were struck by a sudden, spiking high fever, severe abdominal cramps, uncontrollable chills, terrifying hemorrhages, intense blinding headaches, and a deep paralyzing lethargy. It is an absolute nightmare. Within days, one of your close friends who slept in that room is dead. Within 3 weeks, another friend loses his hearing entirely, descends into a rapid physiological collapse, and dies shortly after. You survive, but the victory is entirely hollow. You are left completely deaf in one ear, plagued by a mysterious, agonizing illness that will literally rip through your joints and your eyes for the rest of your natural life. If you read the primary source accounts of that weekend, it truly reads like the inciting incident of a Gothic medical thriller. A creeping, unseen miasma from the earth, rising up to strike down a group of vibrant young intellectuals. It sounds like Victorian horror fiction, but it is a bizarre, deeply tragic, and nearly fatal historical reality. It is the hidden turning point in the life of a man whose name you absolutely know, but whose physical reality you likely do not. Galileo Galilei. Before we peel back the sanitized layers of history to reveal the flesh and blood man beneath the myth, make sure to like, share, and subscribe to Legendary Lives Unveiled. Join us as we explore the intricate, dangerous web of history's greatest minds and the shadows they desperately tried to hide. The contrast between the pristine, mythological image of the father of modern science, the bearded sage gazing serenely through a telescope, and the chaotic, suffering, highly controversial human being captured in historical documents, is staggering. It is a piece of his history that almost never makes it into standard textbooks. The Galileo that emerges from deep medical retrospectives and translated personal letters, including heartbreaking correspondence from his cloistered daughter, is a libertine, a master lute player, a fiercely devoted but flawed father, an unapologetic intellectual troll, and a walking medical mystery. We must dismantle the myth to understand the genius. When you realize the sheer amount of physical pain and political terror this man was operating under, his breakthroughs in physics and astronomy seem like an act of profound human endurance. To build the man from the ground up, We must start with his incredibly confusing name and his surprisingly reluctant entry into science. Born on February 15th, 1564, in the city of Pisa, his name, Galileo Galilei, sounds absurdly redundant to modern ears. But his parents, Vincenzo Galilei and Giulio Aminati, were following a specific Tuscan naming convention of the era. Both the given name and the family name derived from a highly prominent ancestor, Galileo Bonaiuti, a respected physician, university teacher, and politician in 15th century Florence. Families attempting to project pedigree would often name the eldest son after the parent's surname to honor that lineage. Because surnames were somewhat fluid back then, he was often just known as Galileo from Pisa, or Galileo, Vincenzo's son. And to fundamentally understand Galileo's scientific method, his entire approach to questioning the universe, you must understand his father's approach to music. Vincenzo was a renowned lute player, a composer, and a highly influential music theorist. But Vincenzo was an intellectual disruptor who actively rejected the prevailing Pythagorean dogmas of music theory. The traditional view, stretching back to the ancient Greek philosopher Pythagoras, was that musical harmony was perfectly governed by abstract, immutable mathematical ratios. Pythagoras believed the universe was just numbers, and music was their audible expression. If you plucked a string, and then plucked a string exactly half that length, you got a perfect octave. It was mathematically clean, and for 2,000 years, it went unquestioned. But Vincenzo noticed that the rigid theoretical math did not always match the messy reality of tuning a physical instrument. Instead of merely reading ancient Greek texts, Vincenzo set up physical experiments. He proved that pitch wasn't solely governed by abstract length, but by physical tension and mass. He demonstrated this by literally hanging different lead weights from lute strings of the same length and measuring the sound. He discovered that to raise the pitch by an octave, you didn't just double the tension. You had to multiply the tension by 4. This was a massive paradigm shift. Galileo's very first exposure to experimental physics wasn't dropping weights off a tower. It was standing in his childhood home, watching his father prove that revered ancient philosophers were fundamentally wrong, and that truth required physical, empirical evidence. It instilled in him the core idea that you must interrogate nature directly. This environment also cultivated a Renaissance polymath. Galileo mastered the lute with a charmer's style and delicacy of touch, and cultivated a serious talent as a visual artist, deeply considering a career as a painter. He joined the prestigious Accademia delle Arti del Disegno, the Academy of Drawing Arts in Florence, rubbing shoulders with top painters and architects, advising them on perspective, geometry, and crucially, chiaroscuro. Chiaroscuro is the technique of using strong contrast between light and dark to give the illusion of three-dimensional volume. This aesthetic mentality became the bedrock of his astronomy. Before him, astronomers looked at the moon and saw flat, dark smudges, believing it was a perfect, smooth, crystalline sphere. But when Galileo looked through a telescope, his artist's eye, trained in chiaroscuro, recognized the geometric behavior of light. Seeing a bright spot surrounded by shadow, he instantly knew. That is a mountain catching the sun. That is a crater casting a shadow. Yet, this triumphant path was almost completely derailed. Between 1575 and 1578, in his early teens, Galileo was sent to study at the Vallombrosan Monastery, deep in the Apennine forest. Immersed in classical Greek, Latin, and dialectics, he loved the quiet monastic rhythm so much that he entered the order as a novice, earnestly considering the priesthood. But Vincenzo, knowing the family's noble yet precarious financial status, stepped in. Being a monk was a vow of poverty. In 1578, Vincenzo aggressively pulled his son out, using a minor eye infection, an ophthalmia, as a definitive pretext to drag him back to Florence. He needed his son to pursue a lucrative profession, medicine. In 1580, an obedient but deeply unenthusiastic Galileo enrolled at the University of Pisa as a medical student. Medical school in the 1580s was highly theoretical and dogmatic, consisting essentially of memorizing the texts of Galen and Hippocrates, who believed human health was governed by the four humors: blood, yellow bile, black bile, and phlegm. For a kid captivated by the external physical world, it was wildly boring. He was a mathematician trapped in a physician's curriculum. This leads to a highly cinematic moment in 1581. 17-year-old Galileo, ignoring a service in the vast Cathedral of Pisa, watched a bronze chandelier swing back and forth in the air currents. Common sense dictates that a long, wide swing takes more time to complete than a short, tiny swing. But Galileo used his own pulse, the only reliable timing device on his person, to time the arcs. He realized that the time it takes to complete one full arc is exactly the same, regardless of how wide the swing is. This monumental discovery of isochronism proved that a pendulum's period of oscillation is independent of its amplitude, depending only on string length and gravity. This precise observation, made by a bored student using his heartbeat, was the exact mathematical principle that allowed Dutch scientist Christian Huygens to invent the highly accurate pendulum clock nearly a century later. It was the final nail in the coffin for his medical career. Shortly after, he accidentally wandered into a geometry lecture by Ostilio Ricci, mathematician of the Tuscan court. Hooked by the undeniable logic of Euclid, Galileo realized that while medicine was a guessing game, math was absolute truth. He later wrote that the universe is written in mathematical language, its characters being triangles, circles, and geometric figures. He begged his furious father to let him switch his major. However, financial realities caught up. In 1585, Galileo was forced to drop out of the University of Pisa without completing any degree because he could not afford the tuition. Moving back home, he supported himself by giving private math lessons and studying Archimedes. He invented a highly sensitive hydrostatic balance for weighing precise amounts of metals in air and water, using Archimedes' principles of buoyancy. He wrote a brilliant treatise, circulated it, and in 1589, pulled off a stunning academic comeback, returning to the exact same University of Pisa. Not as a dropout, but as the newly appointed chair of mathematics, and it was here that he began his systematic, highly public critique of Aristotelian physics, setting the stage for a dramatic intellectual war that would shake the foundations of history. During his 3-year tenure at the University of Pisa, Galileo began a systematic, highly public critique of Aristotelian physics. For nearly 2 millennia, Aristotle had been the absolute, unquestionable authority on the physical world. He taught that the speed of a falling body is directly proportional to its weight, meaning if you drop a 10-pound rock and a 1-pound rock, the 10-pound rock will naturally fall 10 times faster. According to Aristotelian philosophy, objects possessed an internal desire to reach their natural resting place at the center of the earth. It sounds completely insane to our modern ears, but at the time, that was undisputed scientific law. This brings us to the most famous legend in all of science, the Leaning Tower of Pisa. The cinematic story paints a vivid picture. Galileo, the young, theatrical, and deeply arrogant professor, gets fed up with the stuffy Aristotelians. He drags a heavy iron cannonball and a small wooden musket ball all the way up the spiral stairs to the top of the Leaning Tower. Gathering the old professors in their heavy robes and wide-eyed students at the bottom, he leans over the edge, holds the unequal weights out, and drops them at the exact same time. Boom! They hit the ground simultaneously with a single thud, shattering 2,000 years of dogmatic authority in one dramatic swoop. It is a spectacular piece of scientific mythology, but we must acknowledge the historical consensus. It almost certainly never happened that way. This famous narrative does not actually come from Galileo. It was written by his devoted final pupil, Vincenzo Viviani, in 1654, 12 years after Galileo had died. Galileo himself, a man who obsessively documented every tiny observation he ever made in voluminous letters and books, never once mentions dropping anything from the Leaning Tower of Pisa. Instead, most historians agree today that Galileo's real proof against Aristotle was a brilliant, devastating thought experiment, which he outlined in his early unpublished manuscript, De Motu, or On Motion. The underlying logic he used was so airtight that it mathematically destroyed Aristotle's premise without ever needing a single physical prop. To translate his logic into a modern visualization, imagine a light sports car and a massive heavy garbage truck driving down a highway. In this analogy, Aristotle claims the heavy truck naturally falls or drives faster than the light sports car. Galileo says, imagine tying them together with a heavy steel chain and dropping them both. According to Aristotle's own rules, the lighter, naturally slower sports car should act like a drag parachute, pulling back and slowing the heavy truck down. But the two vehicles tied together now form a brand new, combined system that is significantly heavier than the garbage truck alone. Therefore, according to Aristotle's exact same rule, the combined system should fall faster than the garbage truck by itself. It is a complete logical paradox. The tied objects would have to fall both slower and faster at the exact same time, which is physically impossible. The only logical mathematical conclusion to resolve the paradox is that weight simply cannot be the factor that determines speed. They all must fall at the same speed, regardless of weight, accelerating at the exact same rate. Yet, some push back on the complete denial of the physical drop. A highly respected modern historian, Stillman Drake, intensely defends the idea that the physical tower drop did happen. Drake argues it wasn't a rigid, peer-reviewed scientific test to discover the truth, but rather a flamboyant demonstration for his students, exactly as Viviani described. Galileo already knew the mathematical answer. He just wanted to publicly rub the Aristotelians' noses in it. However, even if Galileo did stand on that tower, the historical timeline presents a sobering fact. He absolutely would not have been the first person to do it. The sources clearly show that a Flemish engineer and mathematician named Simon Stevin performed a rigorous physical version of this exact experiment in 1586, years before Galileo was even a professor at Pisa. Stevin dropped two lead balls, one 10 times the weight of the other, from a height of 30 feet onto a wooden sounding board. Listening to the sound of the impact, he recorded that they hit the board with a single, indistinguishable thud, and he published these findings. Going back even further, to the 6th century, a Greek philosopher named John Philoponus had already written extensively about the idea that bodies of the same substance fall at the same speed regardless of mass. So why does Galileo get all the credit for the law of falling bodies? Because Galileo did the hard, precise math that no one else could do. Dropping objects from a high tower is incredibly messy science. Air resistance plays a massive role, and gravity pulls things down so fast that you simply cannot time the acceleration accurately with 16th century technology. Galileo realized he needed to mathematically dilute gravity. By rolling a perfect brass ball down an incredibly smooth, gentle slope, with grooves lined with parchment to reduce friction, he tipped the vertical drop sideways. This slowed the rate of acceleration down enough so he could measure the intervals accurately. Using a specialized water clock, he weighed the exact amount of water that flowed out of a thin tube during the ball's descent to measure time down to fractions of a second. Through this, he discovered that the distance a falling object travels is proportional to the square of the time it takes to fall. That foundational law of physics, his real empirical proof, came not from a dramatic tower, but from a quiet room with a wooden ramp and a dripping bucket of water. Listening to these meticulous measurements, it is easy to picture a purely cerebral, intensely focused academic living entirely in his head. But his diaries and letters reveal a completely different, almost shocking side of the man. Galileo was a man of immense physical appetites. He was definitively described by his contemporaries as a libertine. He was not a pious, ascetic scholar. He was a great eater who loved rich foods, a heavy drinker who constantly maintained his own vineyards, and a highly sexually active man. Physically, he possessed a strong, square frame, a sanguine and fair complexion, sparkling blue eyes, and abundant reddish hair, and a beard. He was highly sociable, loved to entertain, and thoroughly enjoyed the pleasures of the flesh. This libertine lifestyle, crashing against the rigid social structures of the era, led to a complex and deeply tragic family reality. Throughout the Renaissance, it was fairly rare for high-level scholars to marry, and Galileo never tied the knot. Yet, while teaching at the University of Padua around 1600, which he later called the happiest years of his life, he met a Venetian woman named Marina Gamba. She was a commoner, significantly younger than him, roughly 21 to his 35. Because of this massive disparity in social standing and his own crippling financial anxieties, Galileo deemed it an unhonorable arrangement to officially marry her. Fearing that openly acknowledging illegitimate children with a lower-class wife would destroy his upward mobility and his networking with the nobility, they lived as husband and wife in secret. Together, they had 3 children out of wedlock, 2 daughters, Virginia, born in 1600, and Livia in 1601, and a son, Vincenzo, in 1606. But the brutal, inescapable financial realities of the 17th century were closing in. When his father Vincenzo died in 1591, Galileo, as the eldest son, was left solely financially responsible for the entire extended family. In Renaissance Italy, this included the utterly crushing burden of providing massive dowries for his younger sisters so they could secure social alliances and marry into respectable families. His university salary was wholly inadequate. Constantly hustling, he took in wealthy boarding students, designed and mass-produced his famous geometric and military compass in his own workshop, yet still had to frequently beg for loans to pay the punishing installments on his sister's dowries. He was drowning in debt. Fast forward to 1610. He secures an incredibly prestigious and lucrative position as the chief philosopher and mathematician to the Grand Duke of Tuscany, moving back to Florence. He takes his 2 daughters, Virginia and Livia, leaving his 4-year-old son, Vincenzo, behind with Marina Gamba in Padua. As the girls approach their teenage years, Galileo takes a hard look at his financial reality. Because they are officially illegitimate, unyielding societal rules dictate they would require exorbitant, massive dowries to marry into noble families. Money he knows he will never be able to save. He makes a cold calculation. Both of his daughters are legally and socially unmarriageable. In 17th century Italy, there was only one respectable alternative for an unmarriageable woman of their father's high social standing: the religious life. As soon as they are old enough, he places both of his teenage daughters into the heavily cloistered, deeply impoverished convent of San Matteo in Arcetri to become lifelong nuns. Virginia takes the veil and becomes Suor Maria Celeste, and Livia becomes Sister Arcangela. As a modern observer, looking at this sequence of events feels deeply hypocritical, if not outright cruel. Here is Galileo, living a grand life in Florence, drinking fine wines from his estates, eating luxurious meals, rubbing elbows with the Medici Grand Dukes, buying expensive glass for his telescopes. And he literally locks his own teenage daughters away in a freezing, impoverished convent for the rest of their natural lives simply because he doesn't want to figure out how to pay for a wedding. Yet, we cannot apply 21st century individualistic morality to 17th century familial economics. The social strata of Italy were rigid, unforgiving, and deeply punitive. An illegitimate daughter without a massive dowry faced total social ruin, vulnerability to exploitation, or outright destitution. In the twisted patriarchal logic of the era, placing them in a convent wasn't just about saving money. It was the only guaranteed way to secure their physical safety, their housing, and their spiritual respectability. What is truly staggering is how the daughters reacted. You would expect letters dripping with resentment from abandoned children, but the surviving correspondence from his eldest daughter, Suor Maria Celeste, is some of the most beautiful, heartbreaking, and fiercely devoted writing in history. She is an extraordinary historical figure in her own right, intentionally choosing her religious name, Maria Celeste, as a direct, loving tribute to her father's lifelong fascination with the stars. In her letters, she addresses him with immense formality, most illustrious and beloved Lord, Father, or Sire. Yet beneath that formality, a pure, unconditional love and deep intellectual connection is palpable. The Franciscan nuns at San Mateo were desperately poor, literally forced to bake pastries, spin wool, and grow their own meager food just to survive the winters. And yet, despite her poverty and cloistered isolation, Maria Celeste essentially took on the role of caring for her aging father. She baked him the specific citron pastries and marzipan he liked. She meticulously washed and mended his heavy linen collars and clothes, sending them back and forth in baskets. Astonishingly, forbidden from ever leaving the grounds, she acted as his remote estate manager, writing letters detailing exactly how much wine from his estate he needed to sell that season, managing his social calendar, and gently reminding him to send appropriate gifts for the weddings of aristocratic friends. One specific letter from December 19th, 1625, shatters the image of the aloof scientist. "I'm returning the tablecloths in which you wrapped the lamb you sent. And you, sire, have a pillowcase of ours, which we put over the shirts in the basket with the lid." It is a striking juxtaposition. The man actively expanding the known boundaries of the universe is simultaneously exchanging lost pillowcases and leftover cuts of lamb with his cloistered daughter. Beyond domestic chores, she was his personal apothecary. When the bubonic plague ravaged Italy in the early 1630s, she formulated complex medicines from dried aloe and rhubarb to protect him from the evil pestilence. Fiercely protective of his physical health, she constantly warned him about the dangers of the cold air, likely remembering his vulnerability since that terrifying incident in the wind room. She was unquestionably his greatest confidant, understanding his scientific manuscripts deeply. And when she died tragically from dysentery in 1634 at the age of 33, while Galileo was isolated under his house arrest, he was completely, utterly shattered. During her agonizing illness, he had walked to the convent walls every single day just to be near her. Her loss plunged him into a profound depression, proving he wasn't just a brain in a jar calculating trajectories, but a desperate father who relied incredibly heavily on her emotional and intellectual support. And that emotional grounding was something he desperately needed. Because outside the safety of his family, Galileo had a unique, almost self-destructive talent for making very powerful, very angry enemies. That aggressive public posture truly erupted when he turned his attention away from the earth and toward the sky. It is 1609. Galileo is 55 years old. He hears a vague rumor about a Dutch eyeglass maker who placed a convex lens and a concave lens at opposite ends of a tube, creating a device that made distant objects appear 3 times closer. Galileo does not invent the telescope from scratch, but because he deeply understands the geometry of refraction, he vastly improves it. Within weeks, he grinds his own glass and builds an instrument that magnifies objects 20 or 30 times. His first instinct is highly practical and financial. He takes it up the Campanile in Venice and demonstrates it to the wealthy Venetian merchants. He shows them that with this tube, you can spot incoming trade ships hours, even days, before they are visible to the naked eye. In a maritime empire, this is the ultimate commercial advantage. The Venetians are thrilled and immediately double his university salary. But then, in the crisp, clear nights of the fall of 1609, Galileo does something that fundamentally alters humanity's place in the cosmos. He points the tube up. What he sees through those crude glass lenses instantly and violently shatters the Aristotelian concept of the universe. For 2,000 years, the unquestionable truth was that everything in the heavens was made of a perfect, unchangeable, divine substance called the quintessence, or ether. The heavens were perfect spheres. The earth was merely the messy, corrupt center of it all. But Galileo looks at the moon, and with his artistic training in chiaroscuro, he sees ragged mountains, deep valleys, and massive craters. The moon is essentially just a giant floating rock, just as messy and corrupt as the earth. Then, he looks at Venus, and these observations are the definitive mathematical kill shot to the old system. In the old Ptolemaic system, where everything orbits the Earth, Venus is situated between the Earth and the Sun. If that model were true, from our perspective on Earth, we would only ever see Venus illuminated from behind. It would only ever appear as a thin crescent, never fully lit. But Galileo watches through his telescope over several months, and he sees Venus going through a full cycle of phases, exactly like our moon. He sees a full Venus. The only geometric way for Venus to be fully illuminated, from our perspective, is if it travels all the way around to the far side of the Sun. It was absolute visual proof that Venus orbits the Sun, not the Earth. And if that wasn't enough, he points his telescope at Jupiter. He sees 4 tiny bright stars arranged in a line around it. Over several nights, he maps their movements and realizes they are moons orbiting Jupiter. This is catastrophic for the Earth-centric model. The Aristotelians had long argued that if the Earth moved around the Sun, it would leave its moon behind. Yet here was Jupiter, clearly moving through space, carrying 4 moons along with it. He rapidly publishes all these explosive findings in 1610 in a short, readable book called Sidereus Nuncius, or The Starry Messenger. Ever the brilliant political operator, he names the newly discovered moons of Jupiter the Medicean stars to flatter his former student, the immensely powerful Grand Duke Cosimo II de' Medici. The flattery works perfectly. He secures an amazing, high-paying job as the court philosopher in Florence, completely freeing him from his teaching duties. But here lies the fatal flaw in Galileo's character. He was not just a detached scientist, coolly reporting data. He was a brilliant, sarcastic, arrogant, and incredibly blunt debater. He didn't just want to prove he was right. He had a deep psychological need to prove that you were an absolute idiot for disagreeing with him. Enter his arch-nemesis, a prominent Florentine nobleman and staunch Aristotelian scholar named Ludovico della Colombe. Historical sources describe Colombe as a striking figure, tall, very thin, with a long white beard flowing down his chest, a little bald head, sunken eyes, and a severe, melancholy character. A satirical poet of the time nicknamed him the Superintendent of Limbo. because he was so stuck in the past. Coulomb completely despised Galileo, and the feeling was entirely mutual. When Galileo published his observations of the rugged mountainous surface of the moon, Coulomb panicked. Desperate to save Aristotle's idea of a perfect celestial sphere, Coulomb published a paper arguing that, yes, maybe there are mountains, but all those craters and valleys are actually filled with an invisible, perfectly smooth, crystalline substance that we just can't see, restoring the moon to a perfect sphere. It was an absurd, desperate defense. Galileo's response was legendary and mercilessly petty. He wrote back, essentially saying, "If you can invent invisible crystal to make the moon smooth, then I will use your invisible crystal to build mountains on the moon 10 times higher than before." He mocked Coulomb in public letters, calling him incompetent and delusional. But Coulomb wasn't alone. He began actively rallying a group of disgruntled Aristotelian philosophers, university professors, and conservative churchmen to oppose Galileo at every single turn. This opposition group earned the greatest, most petty nickname in the entire history of science. Galileo's close friend, the painter Sigoli, wrote a letter referring to Coulomb's group derisively as the Lega del Pipione, the Pigeon League. It is a brilliant, multi-layered Renaissance insult. First, it is a direct pun on Coulomb's last name, which translates to the feminine plural for doves. But in the vulgar Tuscan dialect of the streets, Pipione is a vicious triple entendre. It literally means a young fat pigeon, but it was also a jocular anatomical slang term for a testicle, and a common term for an easily duped, gullible fool. It was a highly sophisticated way of calling his academic opponents a bunch of bird-brained testicles. But as funny as it was, the Pigeon League was highly dangerous. They were actively looking for ways to destroy his career, and Galileo walked right into their trap. The debates moved from the sky to the dinner table. In the summer of 1611, at the luxurious house of a mutual friend, Filippo Salviati, Galileo gets into a massive, highly public screaming match with Aristotelian professors over the physics of floating bodies. Specifically, why ice floats on water. The Aristotelians argue that ice is simply condensed water, floating purely because of its flat, broad shape, resting on the surface tension like a leaf. Galileo, relying on the ancient mathematical principles of Archimedes, correctly argues that shape has absolutely nothing to do with it. Ice floats because it is less dense or more rarefied than the liquid water supporting it. The volume of water it displaces weighs more than the ice itself. He boldly states that all bodies denser than water will sink, and all bodies lighter will float regardless of their shape. Coulomb officially challenges Galileo to a public gladiatorial scientific demonstration. Galileo goes home and writes an entire book, Discourse on Floating Bodies, methodically tearing Coulomb's arguments to shreds with geometry and experiments, openly scoffing at their uncritical reliance on ancient texts. But by publicly ridiculing these prominent philosophers, he is setting the stage for a much larger, much more dangerous conflict. The Pigeon League realizes they simply cannot beat his math. So, they change tactics completely. If they can't beat him with science, they will destroy him with religion. This brings us to the precipice of the most infamous clash in scientific history, the Galileo affair. To truly understand what happened, we must discard modern biases about science versus religion and grasp the intense anxiety of the Catholic Church in the early 17th century. The Church was not inherently anti-science. Jesuit astronomers like Christopher Clavius, the man who designed the Gregorian calendar, had their own powerful telescopes and officially verified Galileo's discoveries of Jupiter's moons and the phases of Venus. The Church initially celebrated these observational breakthroughs. The conflict arose entirely from the theological interpretation of those facts. The Catholic Church was violently sensitive to scriptural interpretation because they were in the immediate bloody aftermath of the Protestant Reformation and the ongoing 30 Years' War. The Protestants, led by Martin Luther, had fractured European Christianity by arguing for individual, personal interpretation of the Bible. In response, the Council of Trent fiercely clamped down, declaring that only the Holy Mother Church had the absolute authority to interpret Scripture to maintain order against the Protestant threat. And here comes Galileo, a mathematician, not an ordained theologian, posing an existential threat. The Bible contains passages that seem to definitively state the earth is stationary, most famously in the book of Joshua, where Joshua commands the sun, not the earth, to stand still in the sky. If the earth is spinning, as Copernicus theorized and Galileo championed, it directly contradicts a literal reading of the inerrant Word of God. Instead of staying in his lane, Galileo starts writing open letters, like his famous letter to Benedetto Castelli, aggressively arguing that Scripture shouldn't be read as a science textbook. He uses the theological principle of accommodation, arguing that God simplified the language in the Bible so ancient, uneducated people could understand it. He is playing theologian, offering his own exegesis on how the Church should reinterpret its sacred texts. That is exactly where he crossed the fatal line. The Pigeon League seized on this. Two conservative Dominican friars, Tommaso Caccini and Niccolò Lorini, preached fiery sermons and officially denounced Galileo to the Roman Inquisition in 1615. This leads to the 1616 non-trial, where a panel of theologians determines the sun-centered universe is foolish and absurd in philosophy, and formally heretical. The formidable Cardinal Robert Bellarmine calls Galileo into his residence and issues a strict formal injunction. Galileo must not hold, teach, or defend the Copernican theory in any way. Galileo agrees, retreats to Florence, and stays quiet until 1623, when the political landscape shifts dramatically. Matteo Barberini, an intellectual, patron of the arts, and a man who had written a poem praising Galileo's discoveries, is elected Pope Urban VIII. Overjoyed, Galileo travels to Rome and has 6 long, private interviews with the new pope. Urban VIII gives him explicit permission to write a new book comparing the Copernican and Aristotelian systems. But the pope gives him one strict, unbreakable condition. Galileo must treat Copernicanism merely as an interesting mathematical hypothesis, and he must explicitly include the pope's own favorite theological argument, that God is omnipotent and could make the universe function any way he pleases, so human minds can never truly know how the universe actually works. Galileo spends years writing his masterwork, the Dialogue Concerning the Two Chief World Systems, published in 1632. And this is where his sarcastic, abrasive, Pigeon League trolling nature absolutely seals his fate. He writes the book as a conversation between 3 characters. The character arguing the Copernican view is Salviati, brilliant, witty, clearly representing Galileo. The character arguing the Aristotelian view is named Simplicio, which translates basically to the simpleton or the fool. And in the final pages of the book, into the mouth of this bumbling, foolish character, Galileo verbatim places the exact theological arguments regarding God's omnipotence that Pope Urban VIII had specifically mandated he include. It was a catastrophic, arrogant miscalculation. He had literally called the Pope a simpleton in print. When the Pope, already under immense pressure from conservative Spanish cardinals to be tough on heretics, read it, he didn't just disagree. He felt deeply, personally betrayed, and publicly humiliated. The patronage relationship was instantly shattered. The Pope ordered the book banned and summoned an aging, sick Galileo to Rome to face the full wrath of the Inquisition. This brings us to the infamous 1633 trial. and our historical sources are very clear about systematically dispelling the popular, highly dramatic myths surrounding it. Galileo was never thrown into a damp, rat-infested dungeon. He was never chained to a stone wall. Because of his immense fame and the protection of the Grand Duke, he was housed in absolute luxury during the trial, first in the Tuscan ambassador's grand palace, and later in the comfortable apartments of the Inquisition's high-ranking prosecutor. Furthermore, he was never actually tortured. The historical record shows no mention of physical torture in the highly detailed daily accounts sent back to the Pope. Galileo was nearly 70 years old and in incredibly frail health. The threat of torture, called the territio, was a standard procedural formality of Inquisition canon law to elicit a confession. But it was strictly forbidden to actually torture a man of his advanced age and physical condition. It is also vital to note that despite Galileo's brilliance, there was actually no definitive, undeniable physical proof that the Earth moved at the time of the trial. The stellar parallax needed to physically prove the Earth's orbit would not be visually observed until the 19th century. So, what was he actually convicted of? He was not convicted of heresy itself. The Inquisition focused entirely on his disobedience of that 1616 injunction from Cardinal Bellarmine. The charge was that he had broken a direct legal order. He was convicted of vehement suspicion of heresy, a very specific legal term, meaning he gave the overwhelming appearance of favoring a heretical doctrine by arguing that a condemned theory was highly probable. His sentence was brutal for such a proud man. Dressed in the white shirt of penitence, he was forced to publicly abjure, to literally get on his knees and recant his life's work, swearing he cursed the errors and heresies of the moving earth. His book was universally banned, and he was sentenced to formal imprisonment, which the Pope immediately commuted to perpetual house arrest for the rest of his life. He was also required to recite the 7 penitential psalms once a week for 3 years, a heavy spiritual task that his devoted daughter, Suor Maria Celeste, lovingly took upon herself to perform for him from her convent. The Galileo affair is a profound tragedy of timing, clashing personalities, and institutional rigidity during a time of war. But his house arrest in Archetri wasn't merely a quiet political imprisonment. It was a dark exile marked by a terrifying, agonizing physical decline, which brings us full circle back to that fatal freezing weekend in the wind room in 1593. That freezing subterranean air in Costosa triggered something deep inside his biology that simply never went away. Over the decades, Galileo's letters describe a relentless, compounding onslaught of ailments. He suffered from severe recurrent tertian fevers. In 1613, he wrote about a renal colic so agonizing it was generating sandy stones. He developed a growing, deeply painful inguinal hernia and suffered from severe hemorrhoids that caused alarming blood perfusion. By the time he was summoned to Rome for the trial in 1632, he initially delayed the journey, claiming he was legitimately too sick to travel on horseback. The Pope, suspecting he was faking it, sent 3 eminent Vatican physicians to Florence to examine him. Their surviving medical report is a chilling clinical snapshot of a failing body. They noted he suffered from extreme giddiness, diffused flying pains across his muscles and joints, a severe hernia, at imminent risk of rupturing into his peritoneum, and what they diagnosed under the humoral theory as hypochondriacal melancholy. Crucially, they recorded pulsus intermittens. His pulse skipped every 3 or 4 beats. Modern cardiologists suggest he was almost certainly suffering from chronic atrial fibrillation or an incomplete atrioventricular block, putting him at constant risk of stroke. But the most terrifying affliction, the one that broke his spirit, was his slow, unstoppable descent into complete blindness. It began in 1616, when he reported seeing a corneal halo, halos of light around objects. Over the years, he constantly complained of a fluxion, a recurrent painful discharge, and severe inflammation in his eyes. In February 1637, he completely lost sight in his right eye. By November, the left eye was failing rapidly, and by Christmas 1637, at the age of 73, the man who had quite literally opened up the visual universe to humanity was totally, irreversibly blind. He dictated a heartbreaking letter stating flatly, whether the eyes were open or closed, it was the same. His international supporters were desperate. They compiled a highly detailed description of his symptoms and sent it to a famous Roman surgeon, Dr. Giovanni Trulio. Operating entirely from a distance, Trulio diagnosed severe uveitis that had resulted in a pannus, a thick, opaque skin or mucosity that formed completely over the pupil, blocking all light from entering the retina. Trulio's prescribed treatments were peak 17th century medicine, laudanum pills for pain, and eye drops made of dried aloe, heavy metals like lead, sweet Malmsey wine, and rose water. He even suggested a brutal needle decompression of the eyeball if the underlying cause was glaucoma. What actually caused this cascading physiological collapse? Decades of fevers, migrating joint pains, urethral issues, and finally, blinding uveitis. A fascinating analysis conducted by medical researchers at the University of Padua points to a highly compelling retroactive diagnosis: Reader's syndrome, more commonly known today as reactive arthritis. Think of the immune system as a highly trained military. Reader's syndrome is an autoimmune condition triggered by a bacterial infection. The immune system mounts a defense, but in a small percentage of people, with a specific genetic marker called HLA-B27, the system panics and loses its targeting. It starts unleashing friendly fire on the body's own healthy tissues. It classically presents as a triad of symptoms: severe arthritis, urethritis, and anterior uveitis, the exact specific inflammation of the eye that causes the pannus Galileo suffered from. But what triggered the initial bacterial infection? Given his highly active libertine lifestyle as a young man in Padua, it is entirely possible he contracted a severe gonorrheal infection, a common trigger for Reiter's syndrome. However, there is another highly specific theory, linking directly back to our opening story. The sudden, unprotected exposure to the damp, freezing air in the Costosa wind room could have resulted in a severe acute respiratory infection from the bacteria Chlamydia pneumonia. This specific bacteria is clinically known to trigger the exact cascade of reactive arthritis. Sleeping in that primitive, luxurious air conditioning out of pure convenience might literally have set off an unstoppable chain reaction in his immune system that slowly crippled his joints and ultimately blinded him 44 years later. It is an astonishing, tragic butterfly effect, and yet, despite being totally blind, heavily monitored by the Inquisition, and in constant, excruciating physical pain, his mind simply never stopped calculating. In his final dark years, he dictated his most advanced thoughts to his loyal, brilliant young pupils, Vincenzo Viviani and Evangelista Torricelli, the man who would later invent the barometer. Since the church had strictly banned all of his books from being published in Italy, his supporters covertly smuggled his final manuscript out of the country to Holland. This final book, Discourses and Mathematical Demonstrations Relating to Two New Sciences, synthesized his entire life's work on kinematics, the physics of falling bodies, and the structural strength of materials. It is widely considered the true foundational bedrock of modern physics. Galileo finally passed away on January 8, 1642, at the age of 78, likely succumbing to congestive heart failure and a final bout of pneumonia. But the tragedy did not end with his final breath. Because he died while still officially under the Inquisition's vehement suspicion of heresy, the church strictly forbade a public funeral an oration, or any sort of marble monument. When the Grand Duke of Tuscany wanted to build him a tomb, the Pope threatened him. So, the man who mapped the heavens was quietly buried in an unmarked, neglected tiny room tucked under the bell tower of the Basilica of Santa Croce in Florence. Nearly a full century later, in 1737, the political climate cooled, and the scientific revolution he sparked became undeniable. It was decided to exhume his remains and move him to a grand mausoleum in the main body of the Santa Croce Church, right across from Michelangelo's tomb. But during this nighttime exhumation, the prominent professors and antiquarians overseeing the move decided they wanted holy relics of the saint of science. They literally grave robbed him. Anton Francesco Gori, an antiquarian, took a knife and removed the middle finger of Galileo's right hand, the very hand that pushed the telescope lenses. You can still see that exact finger today, skeletal and pointing upward, housed in a delicate glass and gold egg at the Museo Galileo in Florence. Another professor, Antonio Cocchi, reached into the coffin and removed Galileo's fifth lumbar vertebra, which is still preserved today at the University of Padua. Ironically, when modern anthropologists examined that stolen vertebra, looking for physical signs of the severe spinal arthritis from Reiter's syndrome, they found only mild age-appropriate arthrosis. This suggests his rogue immune system attacked his peripheral joints and eyes far more aggressively than his lower spine, proving he remains a complex mystery, even in death. What does all of this mean? We have traced the arc of a man pushed away from the quiet priesthood, who abandoned medicine to watch a chandelier swing, who built a tube of glass that broke the perfect sky, who trolled his enemies so hard it sparked an Inquisition, and who suffered unimaginable lifelong physical pain. It means that the birth of our modern scientific era wasn't a clean, clinical process carried out by flawless intellects in sterile rooms. It was forged in the messy, politically dangerous, fiercely egotistical, and physically agonizing reality of human life. Science was his only lifeline when his body and society turned against him. Sitting in the dark in Archetri, losing his sight, his mathematical deductions about the libration of the moon, the slight wobbling that lets us peek around the edges of the far side, were so precise that they were only fully visually confirmed in 1959 by the cameras on the Russian Luna 3 spacecraft. From a blind, ailing man trapped under house arrest, to a Soviet satellite snapping photos in the vacuum of space during the Cold War, it leaves us with a profound, lingering question. If our entire modern understanding of the universe, the physics that put rovers on Mars and orbital mechanics that keep GPS satellites in orbit, rests on the shoulders of a man breaking the cosmos open while trapped in a failing human body, how does profound physical suffering shape the way a genius conceptualizes the stars? Does the inherent fragility and painful unreliability of the human body subconsciously necessitate the search for eternal, mathematically perfect truths that never decay? It is a powerful thought to linger on. The stark, poignant contrast between the infinite, orderly, geometric heavens he discovered and the painful, chaotic, and ultimately temporary reality of his physical existence. If you found this exploration of Galileo's hidden life as fascinating as we did, make sure to like, share, and subscribe to our channel, Legendary Lives Unveiled. Drop a comment below on what surprised you the most. Was it the wind room, the pigeon league, or the stolen vertebra? Until next time, keep questioning the world around you.